Assalamu alaikum. Today we will walking you through the beautiful world of Recurrent Neural Network. I am Azmain Sheikh and my teammate,
Assalamu alaikum, I am Jannatul Ferdause.
and let's dive in.
Our agenda: Introduction to RNN, Architecture of RNN, Types of RNN, Application of RNN training and example, Advantages and disadvantages.
Let's begin with a powerful idea. How do we teach machines to understand pattern through time? That's where recurrent neural networks or RNN comes in. They are artificial neural networks adapted specifically to sequence data like time series, text, or audio. Unlike regular neural networks, RNN have something very special, a memory. Each RNN unit includes a hidden layer that remembers important information about the previous step in the sequence. The hidden state involves over time acting as a kind of short-term memory. Architecturally, RNN are built from feed-forward networks, but with a twist. They loop back on themselves. This looping structure allows them to pass information forward through the sequence while reusing the same weights at each time step. But there's more. When an RNN processes a sequence, it does not just look at the current input. It also considers the previous inputs before making the prediction. It gives it a sense of context or temporal understanding. After making a prediction, we compare the outputs to the expected result. The difference, the error, is then propagated back through the time and updating the weights using process called backpropagation through time, or it's shortly we can say BPTT. This is how RNN learn by remembering the past and evaluate the present and improving for the future. So why were recurrent neural networks even created? What was missing from the traditional neural networks? So the answer lies in their limitations. First, feed-forward neural networks simply cannot handle the sequential data. They treat each input as isolated, disconnected from what came before or after. Those networks only consider the current input at a given moment. That's fine for recognizing images or statistics data, but not for anything where order it matters, like speech, sentence, or stock prices, etc. They also cannot memorize previous inputs. They have no concept of time or memory. Each input is a clean state with no recollection of what came before. That means they lose important neighborhood or contextual information which can drastically hurt accuracy in sequence-based tasks. And finally, the architecture of feed-forwarding network is fundamentally limited. There are no loops, no cycles, no way for information to flow through time. So overcome those barriers, RNN were born. Networks designed to remember, to loop, and learn from the flow up of data across time. Applications of a recurrent neural network. Recurrent neural networks shine brightest when working with data unfolds through a time sequence where order, timing, and memory matters. They are designed to capture patterns and dependency across the time steps, which makes them ideal for a wide range of real-world applications. In finance, recurrent neural networks are used model stock prices, transaction records, and loan payment histories, learning from the past trends and predict future movements. In environmental monitoring, they help forecasting weather, track energy consumptions, and interpret sensor data, all of which depends understanding how values change over time. In healthcare, recurrent neural network analyze patients monitoring streams and medical records to spot anomalies, trends, or predict critical events before they happen. And of course, in natural language processing and media, they read and generate text sentences, power speech recognition system, and process video frames for context-aware actions. Simply put, wherever there is a sequence, RNN can be find the rhythm. They help machines not just react but remember. Let's now understand how a recurrent neural network actually thinks mathematically. At every step t, the recurrent neural network maintains something called hidden state denoted as HT. This hidden state is kind of memory snapshot that evolves with every new input. We can describe this evaluation as HT is equal to FW HT minus 1, XT, which means the new hidden state depends on the previous hidden state HT minus 1 and the current input XT. Breaking it down, the contribution from the past is WHH into HT minus 1. The contribution from the current input is WXH into XT. So we combine them like this. HT is equal to hyperbolic tangent of WHH into HT minus 1 plus WXH into XT. Here, this hyperbolic tangent function is our activation function, which helps keep the values bordered and stable. Once we have this hidden state, we generate this output. This compact formula captures the magic. Memory plus input, it's non-linear transformation, and then we get the output. And it's the elegant loop that lets RNN remember and predict step by step through time. This diagram captures the core idea behind the recurrent neural network function step by step through time. Starting from the left, we have x1, x2, x3 and xt. Those are our input vectors at one at each time step. And the h0 is the initial hidden state, usually a vector of 0 or learned values. At each time step, the recurrent neural network performs a transformation, its function of W, using the sample weight of W across all the time steps. This is the key. The network shares weights to maintain temporal consistency. At the time step 1, x1 and x0 are combined using the function fw to produce h1, the hidden state. From h1, the RNN generates the first output y1. This process repeats at the time steps 2, x2 and y1 x2 and h1 are used to compute h2, which give us y2. Then x3 and h2 produce h3, which give us y3, and so on. Notice how the hidden state get passed forward. That's the time memory. Each hidden state HT contains the information from all the previous inputs, allowing the recurrent neural network to remember context. The backlog marks the function of W repeat its repeating function using the same parameters at every steps. That's the recurrent nature of the network. Finally, YT is the output of the last time step. It could be a classification, prediction, or generated value depending on our task. So in short, input flows in from the left to the right, hidden states pass memory forward, shared weights handle learning across the time, outputs are produced at each step. This structure makes a RNN ideal for any data that is time component or sequential.
Now I will discuss how RNN works by an example. Okay. Character level language model. Let's break this slide down step by step to understand how an RNN processes sequences. In this case, a word character by character. We are training the RNN on the word hello, and the vocabulary it understands is HELO. That means each letter is represented as a one hot encoded vector. On the bottom row, labeled input chars, you see the sequence of input characters HELL. Each is turned into a binary vector in the input layer. For example, H is equal 1000, E is equal 0100, L is equal 0010. Next is the hidden layer. This is where the magic happens. When we input the first character H, it produces a hidden state vector 0.727, 0.832, 0.898. That hidden state is passed along to the next step and combined with the next input, in this case E. This process continues with the hidden state updating at every step, remembering context as we move through the sequence. At the top, we have the output layers. The RNN predicts the next character at each time step. For example, after inputting H, it tries to predict E. After inputting E, it tries to predict L, and so on. The numbers in each output block represent raw scores or probabilities for each character in the vocabulary, which are then converted into a predicted character. On the top right, you see the final prediction. After inputting L, the model predicts O, which completes the word hello. The key takeaway here is that the RNN learns the sequential pattern. H, then E, then L, then L, then O. It doesn't just memorize characters, it learns the flow, the rhythm of the sequences. That's what makes it so powerful for language modeling, speech, and any temporal data. Vector sampling at test time. Now let's look at what happens during test time when the model is used to generate test rather than train on it. We are still using a character level RNN with the same vocabulary HELO. During training, we had access to the full sequence like hello. But at test time, the RNN predicts one character at a time. And we feed that prediction back into the model to generate the next one. Let me walk you through it from left to right. Step 1. Input H. We feed the character H into the model using a one hot vector, which is 1000. It generates a hidden state, those three floating point numbers. The hidden state is passed to the next time step and an output vector is produced. Then step 2, output. Raw scores and softmax. The output layer is give us raw scores for each character, not probabilities. Yes. These raw values go through a softmax function, turning them into probabilities. For example, here we get something like 0.1164, 0.4115, 0.254, 0.2177. Step 3, sampling. Now comes the sampling step. Out of the softmax probabilities, we randomly choose the next character. Let's say the model picks E. That prediction E becomes the next input to the model. Repetition. This cycle repeats. The predicted letter is fed in. Hidden state updates. New output scores are produced, and another character is sampled. As shown here, H predicts E, E predicts L, L predicts L, L predicts 0. So this is how the RNN generates a sequence one step at a time, reusing its own predictions at input. It's like writing with memory. Each letter knows what came before it.
Now, let's talk about a quite deadly issue in training deep neural networks, especially recurrent neural networks, called vanishing gradient problem. Imagine our RNN model is trying to learn from long sentences, word by word, step by step. Each step produces a hidden state A0, H1 all the way to HT, and during the training we pass gradients back through all those sentences. from the end of the sequence to the start. But here is the catch. At each step back, the gradient gets multiplied by the weight matrix. If those weights are small, the gradient shrinks. It shrinks again and again until it's particularly zero. So what does it mean? It means the early layers like A0 get no learning signals. The model simply forgets them. It cannot connect that what happened at the beginning to what happened to the end. For an example, it like to trying to remember the first word of a song, hearing 100 verses. The signal fades into silence. This is why RNN struggled with the long-term dependencies. They are great at short memory, like remembering the last few words, but anything further back gets lost in the fog. So how does we fight back against the fading signal, or we can say the vanishing gradient? Here enter LSTM, long short-term memory, a powerful upgrade to the traditional RNN. Unlike the simple RNN that blindly pass information forward, LSTMs are memory architecture. Each cell in the LSTM has 3 carefully designed gates. 1. Input gate. This gate describes how much of the new input should be influence the memory, should it listen or be ignored. At the second, forgot gates. As the name suggests, it decides what part of the past to forget, like decluttering your thought. It tosses out the irrelevant memories. And thirdly, and finally, the output gate. It determines what information from the memory should be passed forward to the next step. Together, those gates form powerful feedback loop, selectively remembering, forgetting, and sharing. This allows LSTM to retain relevant information across the long sequence without gradient vanishing into nothing. But what if we want something learner faster? There were GRUs, the great recurrent units, come in. They are the minimalist of the memory world. GRU combine the input and forget gates into a single update gate and merge the memory and output into streamlined structure. So fewer gate means faster learning, less computational load, yet surprisingly GRU often match LSTM in performance on many tasks. So rather you want the full flexibility of LSTM or the speed and simplicity of GRU, both offer way out the vanishing gradient trap.
There are 4 types of RNN. They are one-to-one, one-to-many, many-to-one, many-to-many. In one-to-one types, there are single input and single output. It's generally uses for general machine learning problems. In one-to-many types, there are single input and multiple output. It's uses for image caption. In many-to-one RNN type, there are multiple input and single output. It's uses for sentiment analysis. In many-to-many types, there are multiple input and multiple output. It's uses for machine translation. There are some advantages and disadvantages of RNN. So first of all, I will discuss the advantages. RNN can handle input of any length. Even if the input size is larger, the model size does not increase to remember each information throughout the time, which is very helpful in any time series predictor. Now the disadvantages are computation is slow, training can be difficult, using ReLU or 10H as activation function can be very difficult to process sequences that are very long. Problems such as exploding and gradient vanishing. That's all. Thank you for listening us, and if you have any question, please do comment or inbox us. Thank you.